Welcome everyone to Ecology Live. I'm Jane Catford, a member of the BES Publications Committee, and from next month, a senior editor for the BES Journal of Ecology. If this is your first time joining us, then welcome, and welcome back to all of those of you who are regular. This is our second in our 2021 series of free online talks about the latest ecological research. There are 12 talks in this series, held every Thursday from now until the end of May. We thank Oxford University Press for sponsoring the whole season of Ecology Live. You can find details of an Ecology Live reading list that they've put together for us, including some exclusive discounts on the slide at the end of the talk today. So do look out for that. Thanks too to Wildlife Acoustics for the lovely soundscape that started this session. This talk is being recorded and will be added to YouTube afterwards, as are all of the talks from this series. There'll be a short Q&A at the end of the talk, so please submit your questions in the Q&A box throughout the talk. There's no need to wait till the end, so get them in nice and early. And your questions can either be named or they can be anonymous. It's up to you. We're very fortunate today to welcome Katharine Suding as our speaker. Katharine is a professor of ecology at the University of Colorado Boulder. She's a highly cited author who has written extensively in the areas of ecosystem dynamics and management, restoration, biodiversity, and conservation. She's a fellow of the American Association for the Advancement of Science, and in 2008, she received the Robert H. MacArthur Award. This is a biennial award awarded by the Ecological Society of America for an ecologist for their pivotal contributions to our field. I've long been a fan of Katharine's work and her approach for doing science, so I'm super excited about what she's going to talk to us about today. So with that, I'll hand over and welcome Katharine as our speaker. Thank you.
Thanks so much. I'm very glad to be here today. I'm going to start. I'm going to start by just saying that it's an honor and it's quite a privilege to be able to speak to so many people remotely. So thanks to the British Ecological Society for hosting this series. Today I want to talk about resilience, recovery, and the ecology of change. And what I really want to emphasize today is how do we maybe further our work thinking about ecology, but thinking about the temporal or the dynamics of change and how that might help us manage systems and think about these constructs like resilience and recovery. First, I want to acknowledge that I'm going to talk about a lot of work and a lot of work that I have just had the privilege to collaborate with a lot of people. So just want to acknowledge many people in my group as well as my collaborators for some of the stuff I'm talking about today. And the people underline in particular, I'm going to talk about their data, and I'll revisit this and give another round of thanks at the end. But without being able to work as a team in science, it just would be no fun, and we would really have not gotten as far as we have. And also, I'd like to acknowledge the groups that have funded the work I'm going to be talking about to enable us to ask these questions. Okay, I want to start here. This is a picture of in the Rocky Mountains where I live, and I want to talk first about how the environment is changing, and I think the idea about environmental change and how ecology as a discipline is going to attack this problem is definitely on the minds of a lot of people. In the Rocky Mountains, just to give a specific example, later today there's a storm that's forecast to come that might deliver over 1 meter of snow. So an unheard of amount of snow in some of these areas. I grew up in Colorado, and I can remember a couple storms, maybe half a meter. So just a record-breaking storm that is forecast to come in. And this is on the heels of a relatively dry winter and extraordinarily dry summer, where we went over a month without any rainfall. I say this because this is happening across the globe, right? We're having changes to our climate, both over more variability as well as more temporal changes. And certainly we're in a climate crisis in terms of all these changes. But on the heels of this, or at the same time as this, we are also in a crisis just as profound in biodiversity. And so we're trying to tackle these issues about incredible losses of biodiversity associated with climate change, but as well as other drivers, land use degradation, pollution, exotic species. And those combined, we're struggling. We're not being very successful. We just finished the United Nations Decade on Biodiversity, and our goals that we set up, we really didn't meet, at least globally. So why is this, and why is this kind of coming to a head? The climate crisis, biodiversity crisis, and how do we move forward, or why are we not being able to deliver? There's a lot of different reasons, but one I want to talk about today is about how we're thinking about management and intervention in these systems. And despite all these this evidence that things are changing quite rapidly in some areas, often our goal in management is to keep ecology relatively unchanged. We use resilience-based strategies to try to absorb change. We're unable to really translate a lot of the adaptation approaches to on-the-ground management. And when we think about recovery, we often think about it in a historic perspective, recovery back to a reference. I want to drill into this a little bit today, because I think this is a sign or a cause of our difficulty to translate ecology and basic theory to address these problems. So some kind of specific examples before I go on. So we think about restoration across restoration projects in a review. Over half of those projects measured recovery relative to a reference condition in a single year and a single site. So a very static idea about how recovery should play out in this world of very rapid change. When we think about resilience and how to make a system more resilient, 86% of the management recommendations are to maintain existing patterns and processes, even in light of this rapid ecological change. And lastly, when there are recommendations for adaptation or allowing change within a system, they are rarely implemented due to high uncertainty and high risk. So even when we recognize the need to take an adaptive approach, we're really unsure how to translate that, to on the ground action. Now we know, on the other hand, based on a lot of constructs in ecology, that change is to be expected, and it actually is a sign of a dynamic, self-sustaining, healthy system. The turnover of biodiversity at all levels maintains function and also maintains the ability of multiple types of diversity to remain in the system, and that diversity is able to be sustainable over the long term. So if you compare these to this dichotomy about, we know that change is to be expected, particularly in these times of rapid ecological change, but often our management goal is to keep ecology unchanged. So what's happening here, and where can we move forward? So I want to suggest that we need to dive further into the mechanisms of temporal change. So how biodiversity changes, and really think about that mechanistically. And if we do understand this, and if we make strides to that, I think we would be far more able to suggest management, intervention, and goals that might break us apart from this, from these scenarios of feeling like the safest management goal is a static one. So when you think about a system, I love this picture. So this is a picture of the Lena River in Russia. We know there's no question about that change is both spatial and temporal. It's the foundation of almost all ecological disciplines. We also know that this is an important problem to tackle, and that just a quick survey, that over 50% of all papers in the ecological category on Web of Science did focus a bit, at least, on environmental change. So we do recognize the problem, and we are pursuing it. But if you think about this dynamic between what we know about spatial processes and how we're using spatial considerations to guide conservation versus temporal considerations, I think we're really overlooking a lot of the temporal dynamics. So if you think about the works that look at spatial ecology versus temporal ecology, I know this is an imperfect metric, but the spatial considerations outweigh the temporal considerations, or at least in papers, about 30 to 1. So I think that we can no longer overlook these temporal considerations, and thinking much more rigorously about the temporal dynamics of change. So I'd like to propose that instead of managing by pattern, we need to look under the hood of these changes over time to the mechanisms of temporal biodiversity change. And by doing that, I think it will enable much better ways to identify how best to manage trajectories of this change. And thinking about this in terms of that, giving some on-the-ground solutions to, at least at the local level, to managers about how to guide, to tweak, to intervene, to passively let the processes play out. All those questions that management in conservation and restoration face. I want to give you a couple of examples about how we're working towards this. But first, I want to just talk a little bit more about what I mean when I say mechanisms of temporal biodiversity change. So if you think about drivers that are occurring across the globe, whether it's over harvesting, pollution, land use change, climate change. We think about a system and think about the biodiversity that it maintains, that these drivers are pushing this system, giving it a kick, and the community, so all these species and interactions, are reorganizing. We know this happens, and this is what results in these trajectories of biodiversity change. The question is, what information do we need to know to be able to manage these? And I would argue that the local intervention opportunities occur at the level of our understanding of the community reorganization. So how these drivers translate through the community and species interactions. And there, that is our lever, at least at the local level, and at least for our managers that really cannot likely not address the external drivers directly themselves. So that is what I am referring to in terms of really understanding the mechanisms. How do these communities reorganize? How do the species interactions change? I'm going to give you a couple examples about how we're doing this and how this might prove to be a pathway in the future. So first of all, I'm going to talk about how we are able to look under the hood and what mechanisms we're discovering when we're thinking about how these external drivers of change are affecting the community and how the community is reorganizing under those temporal conditions of change. Then I'm also going to take that example and try to argue about why it is so much more helpful to understand those mechanisms when we are trying to translate into application. And so what we can do on the ground in order to meet restoration and conservation goals. I also am going to give a little bit of a sense about how we do this and the approaches that are available to use to actually look under the hood. And I do this because the approaches are changing rapidly and there's becoming much more ability to do this, both because we're accumulating longer term monitoring data sets, as well as really advancing theory in order to start understanding these processes. So just to say, I'm going to use these icons. So thinking about the mechanisms, what's under the hood, then the approaches about how we can look under the hood, and then how maybe this approach helps in application. So for a first example, this is from the serpentine grassland in California, a hugely diverse endemic system that harbors lots of important biodiversity. So when we look at the changes due to rainfall, and rainfall is a critical factor in this community, and the increasing variability of rainfall, as well as perhaps the potential of these systems to get drier over time. We find that species responsiveness, so across the community, different species respond to rainfall and rainfall variability. It depends on species interactions and whether the species are rare or abundant. So some species are very responsive when they're rare, but that response to rainfall is dampened as they get more abundant due to self-limitation and competitive factors. Other species, actually their response to rainfall is actually amplified as they get more abundant through changes in species interactions. Why is this really important when you're thinking about changes in rainfall variability? Well, the idea that some species populations will be really variable, and if rainfall variability increases, that their population stability will also decline and will get more and more variable, versus some other species actually we shouldn't really care about that as much, because they are their stability occurs because of their the interactions in the species, in the community. So how did we look into this? So approaches, we can take long-term observations of, in this case, count over time, long-term data set, but these data sets are becoming more and more available. And because we have information about all the species in the community, as well as rainfall under these different conditions. So high rainfall levels, low rainfall levels, with different species abundant or rare, we can use the patterns over the last 30 years to infer the effects of rainfall, as well as inter and intra-specific effects through demographic models. And what does it matter? So why would this matter to be able to say something about species responsiveness to rainfall and conservation in this system? Well, it turns out that when thinking about how to conserve rare species and thinking about a stochastic factor like rainfall, really concerned that species variability in their populations will put them at risk of extinction. But now we know, when we look into this, these associations, that there are actually rare species that are very stable, that aren't very variable due to external conditions like rainfall. And those maybe we don't have to worry about in terms of low population sizes as much as the other species where the variability, the rainfall variability actually amplifies their stochastic population fluctuations. On the flip side, we also can use this information to think about how to best control the invader in this system, which is a brome grass. And its population is actually very responsive to rainfall. And so the idea of intervening and trying to control its population, removing it, weeding it, is much more likely to be successful in periods after, in dry periods where its population growth rates are actually very diminished. So moving on to another example of another system. So now here's an example from alpine tundra in Colorado, where we find that the system structure in terms of, and then how it responds to environmental change, that environmental change reduces stabilizing niche differences. So the ability of species to partition resources and maintain diversity. And so these environmental changes increase the potential for competitive exclusion. And this is all across the board, but it's most strong in the abundant species. How do we do this? We use a little different approach, but related, and you'll start seeing some patterns. So thinking about long-term observations, this is across almost 2 decades of work, combined with experimental manipulations. And in this case, in this system, interested in the effects of snowpack, temperature, and nitrogen availability. And because of these long-term manipulations and observing how the community changes over time, we can look at the direct effects of these drivers, as well as how they're causing the community to reorganize. And what does it, why would this matter? Why would this this matter more than just realizing that these drivers are causing a diversity reduction? We're using this information to try to extrapolate how species are going to move uphill in the future scenarios in these high mountain systems. And actually realizing that some species will be able to move uphill due to competitive release, but there's other species that, because of the reduced ability to partition resources and niche differences actually might be really at risk and maybe not be able to move uphill. And those are the ones of conservation concern that we're trying to identify. Another example, so this is back in California, thinking about native grasslands. These native grasslands are form these patches across the landscape and are of a main restoration priority. So they are one of the few relic native grasslands that persist in this region. So when we look at the interactions here and the mechanisms for how these grasslands change over time with environmental pressure, we find strong evidence of feedbacks, so plant soil feedbacks that allow the persistence of these grasslands even when there's external pushes. So this creates a path dependence in both recovery and invasion. So there's areas that are able to resist change through these feedbacks. But once that change occurs, it's very hard to get these systems to recover. How do we look at this and look at this approach in terms of figuring out the mechanisms of this pattern? We use a manipulative approach, reciprocal invasion when rare. So we can create these communities, invade the other types, so invading the native into the exotic community, vice versa. And then along a gradient of environmental change. And in this case, we're looking at a gradient of end deposition. And looking across a gradient allows us to determine these non-linearities and this path dependence of recovery and invasion. And why does it matter? Why would this matter more than just realizing that these native grasslands are really at risk? Well, we can work with groups to identify native grasslands that are persisting and even persisting in fairly high levels of nitrogen deposition, which are associated a lot with pollution due to driving in this system. And we can identify those and place very high conservation priority on those. We do not want to destroy those feedbacks and those legacy effects. And so we've mapped and putting high conservation priority there. And then thinking about restoration, about where these grasslands actually can be recovered, that the only way to do this would be to reestablish those feedbacks. So thinking about both the plant system as well as, in this case, the soil microbial system. And that there's some areas, because of this path dependence, of such high impact that we really can't suggest a reason or a mechanism about how we can get these native grasses back into the system. And so thinking about alternative goals and alternative futures here. And a last example, in rangelands throughout California, I'm trying to understand the mechanisms behind a pattern that is very classic here, where there's some years that are called forb years, some years that are called grassland or grass years, and finding out that climate variability maintains this functional diversity in grasses and forbs via competitive release. And that release is due to these occasional fall droughts that allow the forbs, who are the rarer, less competitive species, to persist. This is important to understand these dynamics because this is a rangeland where the overall forage production matters to ranchers and to be able to sustain system services. How do we do this? It's this pretty similar approach, thinking about how to manipulate both the experimental gradient in terms of drought, as well as the type of interactions that the species are interacting. So this time using a response surface. This combination of experimental techniques and observational techniques are absolutely possible to understand these mechanisms. And then why does this matter? Well, we can model out the historical climate patterns and then also forecast in the future. And because the combination of the grasses and forbs do maintain high forage production, that this system is at risk of losing, in this case, the forbs from the system, if weather patterns occur where there's multiple wet years and we lose this fall drought. And under those situations, we know, or we would recommend that ranchers actually change their grazing practices and graze even harder on those multiple wet years to try to release the forbs and keep them in the system. I hope that gives a little bit of idea or kind of a flavor about the importance of temporal dynamics, as well as how those temporal dynamics can translate into real usable knowledge that we might not really get if we just know the pattern of change. But knowing why things are changing and how the community is reorganizing allows us to figure out how to intervene and whether and what kinds of management techniques might be most successful. So these four examples, the mechanisms all differ, but they all strongly support that we can't just look at environmental change without thinking about the community, the species associations, and how they're changing as well. Talked about several different approaches, but the baseline is that observational data sets are really becoming more and more valuable, and we shouldn't overlook their value in inferring these types of dynamics, particularly when combined with experimental approaches that manipulate species interactions and environmental change, which are there, we're doing them. And then lastly, that with knowing these mechanisms, we really can better understand what interventions are possible. How can we guide these trajectories of change? And what does success look like? Well, thank you very much. I'm glad to be able to share some of these ideas. For more information, these are the papers that I cited today, and particularly the last four are the four papers to look at if you want to see more detailed results of these examples that I spoke about. I also want to thank again and highlight the leads of all these papers, just really exceptional people to work with, and I thank them as well as all my collaborators. Thank you.
I always feel compelled to clap after these talks, even though we are doing this online. Thank you so much, Katharine, for such a fascinating and compelling talk that you've given us. A bunch of questions have come through. I won't be able to get through all of them, unfortunately, but we'll cover some now. So Mariana Garcia Criado has asked, in biomes like the tundra, where change is happening so fast in recent years, what do you think should be a baseline to consider for restoration or conservation efforts?
Well, I think that hits at this major challenge that we're at. I don't think that in many places, particularly when there's rapid change, that we can actually expect a baseline and expect no change or going back. And so what do we do? I would say that understanding how we can maintain the diversity that we have and also understand what we can do to actually maintain some of the species that might be more at risk with these environmental changes. So assuming that we can't intervene to stop warming or changes in precipitation. Hopefully we do that too. And so some of those techniques depend on the mechanisms. And so that's the key there. Some of the techniques that are possible are doing things to reduce the dominance of the abundant species, if that is a strong mechanism. Some of the other techniques that absolutely can be done is to actually boost the population dynamics of the rare species, seeding, planting, putting in some disturbances. But that depends, right? It depends on the types of mechanisms that are causing these changes.
Great, thank you. Santiago Ordonez asks, is it possible for resilient strategies and plans to be scaled up? And what could be possible constraints for this?
That's a great question. And the scaling up, I have to say that a lot of what I've talked about and concentrated on is really local patterns, local mechanisms, and then also local interventions. And so how we scale this up, I feel like then species movement on the landscape becomes paramount, right? And so change at one place actually could be relocation in another place. And so that is the key, I think, to resilience at larger scales, is to incorporate that aspect as well as the effects of local interactions.
Jessie Woodbridge asks, do you think there is potential for paleo-ecological data covering multiple millennia to inform management?
I think so, and actually I'm part of a group I'm looking forward to working on to better understand these dynamics. I think one question is, when does novelty kind of arise, and then what happens, right? And what are the dynamics that actually lead to, people are really concerned about these changes that lead to like a complete collapse of the system and like total reorganization versus more transitions and turnovers. We don't really know this, or we know this just by what we're seeing now. And so to better understand how those dynamics might look and whether there are warning signs for these situations of really strong transitions or transformations and collapse is one area that I'm super interested in.
Thanks. And maybe I'm going to, if it's okay, we'll just do two more questions. There's some really great ones coming in. So Jonathan Wood asks, well, says, you've shown some great examples where you've generated usable knowledge and what interventions might be successful. Have you been able to go on and show success in these systems with the interventions you've recommended?
It's a mixed bag, and absolutely, it's a challenge. So a lot of the interventions that we're able to succeed in have to do with where to conserve, and also being able to implement management disturbances that are levers that are doable. So mowing, the fire's been declining, so we're not using that as much. And then also grazing is turning out to be a successful lever in many cases. You know, the one type of dynamic when we find that it's important that we're really stuck with is interactions that are dictated by plant-soil interactions in the microbial community. I feel like when we find those as being the important constraint, we haven't quite figured out what to suggest to managers. I think it's really hard. The one thing that's looking really exciting right now is seed coating technology, and actually being able to put in species that have seed coats that perhaps even we can kind of like start the soil microbial partnerships that way, maybe more explicitly, as well as change some of the local microenvironments to allow those recruitments. So that might be one other way that'll allow us some success when we haven't found it.
Great, thanks. And the last question, Katharine, before we release you from this, Daniel Oro asks, what would be, in your view, the suitable temporal window to avoid a biased interpretation of ecological processes occurring in a certain ecosystem?
That is an awesome question too. I guess I would give a pragmatic answer to that. We're starting to get data sets that are decades long. We should not ignore those data sets. We should use those. We need to move forward on this, and we really need to provide some at least attempts at solutions. So that kind of constrains our time series in some ways, right? But I think a couple decades and the variability there usually overlaps pretty well with what our future projections are. And so I would say that's better than nothing. Using environmental manipulations, I think, is also something that should be on people's minds to kind of go out of that framework and almost speed up the process. There's issues there, right? I don't think we're going to get that exactly right, but I think that's the best right now. And then just understand how we're using those lines of information as inference, right? And then learning from there.
Fantastic. So thank you so much again, Katharine. I'm sure that 300 or so people are on this call are all quietly clapping for you at home, so which would be a raucous applause normally. And thank you everyone for joining us. There have been some really great questions that have come in, so I'd encourage all of you to get onto Twitter and ask Katharine your questions there. And so her Twitter handle, she's kindly agreed to answer these. So her Twitter handle's in the chat. And you can use the Ecology Live hashtag when you post your questions as well. So thank you once again, Katharine. And thank you. You got up nice and early to give us this talk, so we really appreciate that. Okay, so next week we have another speaker. We are delighted to be able to introduce to you Stefano Elesina from the University of Chicago, who will be exploring a century of the Lotka-Volterra model. So if you're watching this recording now on YouTube, but you'd like to join us live for future events, please go on to the Ecology Live events page on our BES website and register for future talks, and then you'll get invitations directly to your inbox about all of these ongoing talks. Now, if you're a member of the BES, we urge you to keep an eye out for your copy of The Niche this week. The Niche is our quarterly society magazine written by and for our community. It covers the science of ecology and the lives of ecologists through news, opinions, interviews, reviews, fiction and more. And it's a great, I love receiving it, the most exciting mail that I think I now get in my mailbox. The latest issue features our amazing photography competition called Capturing Ecology. There's a roundup of everything an ecologist needs to know, apparently, about politics this year, and a profile of conservation work in Nigeria, protecting the endangered Prius monkey. So if you're not already a member to the BES, you can still receive a copy of this digitally if you sign up today. So head to the link that's been posted in the chat now. And finally, I'll leave you with the details of the offer from the sponsors of today's Ecology Live talk, Oxford University Press. Use the discount code in the chat to receive 30% off their Ecology Live reading list. And that brings Ecology Live for today to a close. We look forward to seeing you all again next Thursday.